This is Ayush, and today we are going to discuss search in rotated sorted array question. And so let's read the question first. There's an integer array nums sorted in ascending order with distinct values. So prior to being passed to a function, nums is possibly left rotated at unknown index, uh, such that result k is between 1 to nums of length, and such that resulting array is this. Right. For example, the example is given. So this is just definition of rotated sorted array. If you don't know what a rotated sorted array is, which please watch my previous video. I have explained it in that video as well. So uh, the simple problem statement is that we are given an array integer array nums. After some possible rotation, it is sorted, and we have an integer target. We have to return an index of target if it is in nums. If it does not exist, then we have to just return -1 if it is not in nums. So we have to write an O of log n runtime complexity algorithm. So, and this question is very important in terms of interviews. As you can see here, like I have this company list. This is asked in so many of the companies, like you can see Paytm, PayPal, and like all ServiceNow, Tencent, D-Shop, Apple, etc. This question is asked a lot. So this question is pretty important. It is asked in Samsung as well. Yeah. So you can, so let's discuss how do we actually solve this problem. So this is our array and these are my indexes. I've written it on top. So our goal is to find the target. Okay. The brute force approach, if this question comes up in interview, you need to tell brute force approach first. So what is the brute force approach? You can simply do a linear search. And find the element. You'll go through each element like 4, 5. Is it equal to target? No. You'll move on, and move on. You now found 0 at index 4. You'll return 4, right? But this is a linear search. And this would take me O of n time complexity, right? Which is something we don't want. As the problem explicitly states, we need O of log n complexity, and interviewer also expects O of log n complexity when you solve this problem. Okay, so how do we do it? So if you are new to this, please watch my previous video, which is on find minimum in rotated sorted array. You can see this question is very related to this, so please watch that video first. Please solve that problem first, then come to this. As you have saw in previous video, that we can find minimum of our rotated sorted array in like O of log n complexity, right? Like let's say I know the minimum from the previous function itself. I know the minimum. This is my minimum, right? So let's say I know the minimum index of the minimum element. So I can just divide my array into two parts. This is the first part, and let's make it the second part here. Yeah, so these are the two parts of the array. If you look carefully, this part and this part are independently sorted, right? This is my pivot, the minimum element, and this is my the starting element, right? So the complete array itself is not sorted, but it is rotated sorted. So when I find the pivot here, that is this element itself, I can see that my array is like these both subparts are independently sorted. So what I can do now is apply binary search to these both parts independently. Just write, if I apply binary search on these parts independently, we get the solution, right? As if my target is 0, right? So I'll apply binary search on this part from index 0 to 3 and check if I find 0 or not. And then I can also search in right part as well, the blue part here. I can check again by applying binary search from index of nums of 4 to nums of 6 if I find my target, which is 0, or if I find my target or not. So this is pretty simple. If you just we just were able to find the minimum, but this requires three binary searches. The first binary search is for finding minimum, right? Second binary search would be binary search on first part, and third binary search would be binary search on second part of array, right? With these three binary search, you would be able to like get the answer. So what we can do is just use the previous function which we have did for finding the which we used for finding the minimum of the rotated sorted array, and we can apply binary search on first part using lower bound function. Again, we can apply binary search on second part using the lower bound function again. So let's quickly do it. I'll just write the code here because it is very simple. Yeah, so this is the first approach. You can mention this in interview as well. The second approach would just require one binary search. We'll discuss this later, but let's write the code for first the first approach itself. Okay, so I have this function which I have written in previous video, that we find minimum of this rotated sorted array. Let's modify this function a bit. Let's rename it to find minimum index. So let's initialize our low and high to this and minimum index to this. Let's initialize to 0, and if I find minimum index, then I'll just do it, assign the index mid here. Got it? So this function would return, okay, now this function would return me the position of minimum element, right? So this is just from previous video, so I'll just write my min index to be, use this function, pass the nums array to it, and I can apply now two binary searches. So now my sorted halves, sorted parts of nums are from low to mid to actually min idx, right? Min idx minus 1, because from min idx we would start our second half, and min idx to actually n minus 1, not low and high. We just need 0 to n, min idx minus 1, and min idx to n minus 1, right? So I can just apply two binary searches. Let's call low bound function auto lb1. Let's call low bound, we can have a starting point which is nums.begin for a 0th index, and second is like something just like one just greater than last index I have to search, so it would be nums.begin plus min idx, right? And for second low bound, it would be nums.begin. The second half would be starting from min idx, so I'll just do a min idx here, and end would be nums.end, right? If you are confused about low bound function, just watch my video on low bound and upper bound functions. So these are my two functions. So if now these functions are executed, they have executed binary search. Now if my low bound one is not equal to nums.end, and then if I dereference it, the value of low bound lb1 is equal to target, then we have found the answer. I'll just return the index which is lb1 minus nums.begin, right? Else also if again for checking the second low bound, if lb2 is not equal to nums.end, that means we can dereference it, so we can check the value lb2 is if lb2 is equal to target, then I'll just return lb2 minus nums.begin. This would give me the index, right? And if both of these if conditions fail to execute, that means we don't have an answer. I'll just return minus 1. Let's run this now. Okay, I need to pass target as well, third argument as target. Yeah, now this should run fine. as you can see, this is accepted. Let's submit it as well. So it is accepted. Yeah, but this approach requires required 3 binary search, right? Can we do better? Yes, we can. So let's actually switch back to iPad. Yeah, so this approach required 3 binary searches, which is fine, but it is technically of log n complexity itself, but we can do better in one binary search itself. How? Let's think. So actually, let's make copy of this array. This was our nums 4, 5, 6, 7, 0, 1 and 2, right? So how can we do this in one binary search? This is our new goal. So let's say you need one observation here. One thing you need to learn is that you don't need everything to be sorted to apply binary search. This is like very misconception around binary search. If you have a sorted thing, then you have to apply binary search. See, the most important condition for binary search is not that array should be sorted, but it is something you should be able to eliminate one half in one iteration. You should know if you have low, high and mid. You should know which half you can eliminate. Can you eliminate low to mid or mid to high? You should know this. If you are able to eliminate each half of the search space in each iteration, then you would be able to apply binary search and you would be able to get answer from the binary search. Okay? Alright. So let's consider this array. I have drawn the graph of this array as well. So as you can see, this is the graph of the array. On x-axis, we have the indexes, which is 0, 1, 2, 3, etc. And on y-axis, we have nums of idx, right? So there's one simple observation I need you to make here. Just observe, if I pick, let's say, any index, let's say this index. So from 0 till this index, this half would be sorted, this part would be sorted, and from here to here, this is unsorted. Okay, let's consider this index now, and you can see that this half, right half, is not now sorted, and the left half is now unsorted. Like this is also sorted, which is good, no problem. And let's consider 1 now. So from like from beginning 0 to 1, this half is not sorted, as you can clearly see that after 7 we have 0, which is just saying us this is not sorted, and the right half, which is just 2, it is sorted, right? So you can look at this observation by graph as well. So let's look at the graph. So in graph, like if you look at any index, let's say this, you can see that one half from like beginning to end, and this is from consider the mid itself as well in this half, and from mid plus 1 to end, one half is always sorted. In this case, this one is sorted, like this one is not sorted, right? As this is increasing here, and this then it decreases, right? So this half is, second half is not sorted, first half is sorted. In the mid we have considered. So now let's consider something here, right? So if I consider something here, so this range, consider this range. Is this range sorted? No. Our elements are first increasing, and then we decrease and then move here. So this half is not sorted, left half is not sorted for this mid. And for now, consider mid plus 1 to like last element. So this range, can you see this is sorted? Yes, it is sorted. Now let's have one more example, just to have a crystal clear understanding of why at least one half of the array would be always sorted. So if I consider the fourth index itself, so the left half including the mid, so how is my graph for left half? It is increasing and it decreases. So this is not sorted. Now from a mid plus 1 till end, this half, as you can see, this is clearly sorted, right? So the point of this explanation is that if you pick, I'll just erase the graph and write it down. If you pick any index, you would divide the array in, you can see the array in two halves, right? The left half and right half. Basically 0 to the index till, and the second half would be index plus 1 till last. Let's call it high itself. So at least one half, at least one half would be always sorted. This is the property of rotated sorted array. So you can look at multiple examples, try it out yourself to understand more. But yeah, let's actually write this down. One half of actually search space would be always sorted. We proved this observation by taking examples of index. So the second point, like how can we use this to our advantage? I just told you how to use binary search. Now we have to eliminate one half. We should know where our target lies. To eliminate one half, we should know which half should we keep, which half is our actual answer, which half, in which half does our answer actually lie. So let's now actually think of the let's try in the example itself. So let's consider this is my low and this is my high, right? So this would be my mid. So now let's check which half is sorted. Is my low to mid sorted, or is my mid plus 1 to high sorted? I can see that my low to mid is sorted. How? It is pretty simple. I'll just check, is my nums of low like smaller than my nums of mid? If this condition holds, then I can say my left half, which is basically low to mid, is sorted for sure, right? And if this condition does not hold, that means if this condition does not hold, then right half is sorted. Let's write it down so we have clarity. If it does not hold, which implicitly means my right half would be sorted. My right half, which is from mid plus 1 to high, would be sorted, is sorted. So at most, so at least we would have one sorted part, or at most we would have like both of them would be sorted itself. That can be the case as well. So what were we? So I can now just clearly see one of my half would be sorted and one would be unsorted. So let's come back to our example. I will check that is my mid equal to target, is my 7 equal to target? No. Then I would have to eliminate one half. I would need to eliminate one half. Now I have deduced by checking this condition that my nums of low is like lesser than nums of mid. It's basically lesser than nums of mid, which means that my this half from low to mid, this half is sorted. And for our convenience this time, our right half is also sorted, but left half is sorted for sure. We can consider this half unsorted for now. Okay, for now. So what I'll check now is my target lying in the sorted half? So if my left half is sorted, I'll just check, does my target lie in this left half or not? So to check if my target lies in the left half, I need my target to be less than equal to, nums of load should be less than equal to target, and also my target should be like less smaller than or equal to my nums of mid. If this condition holds, then I know my target lies in the left sorted half, right? So in our example, does my target lie in the left sorted half, this half? I can check that. No, it does not lie. It does not, 0 does not lie in this range. So I would search right. I would search in right sorted part. I can eliminate this half and I can search right. So I'll just update my pointer low to be mid plus 1 so I can be able to search right. This would be my mid plus 1. Now let's repeat the procedure again. Also for a single element is also sorted, so let's consider this equal to case as well. So if when my nums of low and nums of mid are equal, then also I'm considering a sorted array, because a single element just like 3, this is sorted. The low, high and mid would be this, so I can consider this sorted as well. Anyways, let's move on with our example. So now our mid is this. I'll check, is my mid equal to target? No, my mid is not equal to target, so I would have to continue the search. I would have to eliminate one half. Now let's consider this half. Is my left half sorted? Yes, my left half is sorted now. So what I'll do is I'll check, does my target lie in this sorted half? Yes, 0 lies in this half. I'll check this I'll use this condition, right? By checking this condition, I can see that 0 lies in my left sorted half. So now I will trim down my right search space. I'll move my high pointer to mid minus 1. I'll search in the left search space itself. So I'll just move my high to be mid minus 1, which would be here, right? So this is my low, this is my high, and this would be my mid itself, mid as well. So now I'll just check, is my mid equal to target? Yes, as we can see that mid is not equal to target, we would just return. And uh and yeah, I think that clears it. If basically I can just say that I would just look which half of my array is sorted, and I would check, does that target lie in the sorted half? If my target lies in that sorted half, then I would search in that sorted half. And if target does not lie in that sorted half, I would search in another unsorted half. I know for sure that target does not lie in the unsorted half now. I will have to search the unsorted half now, right? And like we will write the right case as well. We didn't find our needed the right case in our example, but I would write the case as well. If my right half is sorted, and if target, this is just casework I am building upon one by one to solve the problem. You should also build the casework like this in interview if this problem is asked you in an interview. So if target lies in this right sorted half, right? If target lies in this right sorted half, then it should be my nums of mid plus 1 should be lesser than my target, lesser than or equal to my target, or you can just do nums of mid is lesser than target, and target is lesser than or equal to nums of I. This means that my target lies in the right sorted half, and if it lies in the right sorted half, I would search in right sorted half. If this condition does not hold, and right half is sorted, then I know, if this condition does not hold, then I know that my answer does not lie in the right sorted half. I would now instead search left. I would search left instead, right? So this is the whole intuition, and how are we approaching the problem, how are we dealing with the cases, and this is the casework. Let's write the code so we would understand it more clearly. Okay, so let's write the simple code for the same problem. Now I'll initialize my low to 0 and high to be n minus 1, where n would be my size of array. So nums dot size, right? And we will write our binary search as low is less than equal to high. Int mid equals to low plus high minus low by 2, right? So if my left half is sorted, so before that I'll just check if my nums of mid is equal to target, then clearly we found our answer, and I'll just return mid. if we didn't find an answer, I'll check that if my left half is sorted or if my right half is sorted. So check my left half is sorted, I can just do this. If my nums of low is less than equal to my nums of mid, we are using equal to here as well because a single element is also sorted, right? This is also sorted. So let's say left half is sorted, and if my target lies in this sorted half, so if my target lies in this left sorted half, I'll check that. To check that, I can just do simple if else check, which is my nums my target should be greater than equal to nums of low, and my target should be smaller than nums of mid. Equal to, we don't have to put equal to here because we have handled this case separately. And if it lies in like left sorted half, I'll search left. So to search left, I'll do high equal to mid minus 1. Else I'll just do low equal to mid plus 1. That is, my target does not lie in this left sorted half. I would search in unsorted half, which is right half. So to search right, I'll just do a low equal to mid plus 1. Else I can say my this else basically means I have my right half is sorted. So I'll check, does target lie in this right sorted half? So if it does, then for checking that, my nums of mid should be less than target, and then my target should be less than or equal to nums of high. If this holds, basically my target lies in this range, which is mid plus 1 to high, right? So I'll search in right, so I'll just update my pointer equal to low equal to mid plus 1. And else if it does not lie in right half, which is sorted, then I would have to search in left half. So I'll search in left, I'll just update my high to be mid minus 1. And with that, if I do not find any answer, if eventually the target exists, then we will return via this statement. And if we exhausted our search space and we did not return anything, then at the end, which means that we didn't find anything, didn't find the target, so I'll just return a minus 1. So let's try to run it. Okay, let's submit it as well. Yes, so it is accepted. So yeah, that's it from my end, and thanks for watching.